Having seen some examples now of the method of undetermined coefficients, it makes sense to sort of regroup and ask, well, okay, can we formalize the process a little bit? And we absolutely can. The first step is to put the differential equation in standard form. So we have our nth derivative, some coefficient, the n-1th derivative, and so on. And whatever is on the right-hand side has no y's in it. So that right-hand side is the part that has no y's and is only a function of t or x. The next step is to identify the functions on the right-hand side. So if there's a function on the right-hand side, then it needs to be in y. However, that's not enough. We also need to know what other functions might show up in the derivatives, and we call that the differential family. It's the set, so it's a group of functions, just isolated sets of functions, whose combination makes up the right-hand side, and, here's the key thing, all its derivatives. We'll take a look at examples in the next page. For now, assuming we can find that set of functions, then we simply define our solution as a linear combination of all those functions, and we see what we get. Once we've defined our guess at the solution, we sub it into our equation and we solve for those constants, or we determine the constants. It's important to notice we also solve for constants in another phase of this process, but when we're looking at the non-homogeneous part, you do not need initial conditions. That's usually used for the C1, C2, etc. in the homogeneous solution. We'll still need to do that. We have not completed a general solution yet, but that's not what happens at this stage here. So with some practice, this will be clear. These are just ideas to keep in mind as you're trying to familiarize yourself with the process. Going back to that idea of the differential family, which again is the functions or a set of functions on the right-hand side and its derivatives. Right-hand side's derivatives. If we take a look at this example here where the right-hand side is e to the 5t, then e to the 5t, this is a little set notation here, is the right-hand side, is all that's needed for the right-hand side and its derivatives. If I differentiate e to the 5t, I just get more e to the 5t's. And so in that scenario, our y for the non-homogeneous part would just simply be some constant times e to the 5t, and we'd be done. In this next example, we notice there's two functions, t and 1. So the set we need is definitely t, and definitely, we'll call it a basis function 1, and there the non-homogeneous guess of the solution would look like a times t plus b, if you like, times 1, and that would be the general form. Notice nothing at all changes. If I took out this plus 1 and just had t, I would need t because it's in the right-hand side, but the derivative of t is a constant, and so I would need this 1 regardless. As long as I have the t, I'm going to need t and 1. Likewise, if we had for t to the 4th, then the set that we would need for that would be t to the 4th. We might have t cubes, we might have t squareds, we might have t's, and we might have constants. We might have all of those in the derivative. And so our non-homogeneous would be some long combination of t to the 4th plus bt cubed plus and so on, all the way down to the constant term. So that's what we mean by the differential family. It's not just the functions in the right-hand side, but them and all their possible derivatives. And we just look for a simple basis set. We don't worry about 2t cubed or 5t cubed. We'll put constants in front later. What we're looking for is a minimal set that could be used in linear combination to make up the right-hand side and its derivatives. We'll see that more explicitly in this last example. If we have cos on the right-hand side and cos of 3t, then cos of 3t has to be in our set. But its derivative would be sine 3t, so we need that too. But we don't need anything else because the derivative of sine gets back to cosine. However, we do need something for the t squared, and we also need something for its derivatives all the way down to 1, after which the derivatives become 0, and they wouldn't be part of the solution here. That leaves us with, in this case here, a quite a long, complicated, non-homogeneous solution, but that's okay. It's just a linear combination of all 5 of those functions, plus dt plus an e. Using that as a solution, we could plug it into the differential equation and solve for the 5 equations, because we'd actually have 5 functions underlying this. We'd end up with 5 equations and 5 unknowns. Having seen that, let's apply those ideas and find now what we haven't done in a little while, find the general solution to a non-homogeneous equation. All the part that we've been working on so far has been this non-homogeneous part, but we can't forget that there's going to be all the homogeneous solution parts, which we're going to call YC here. So we need to find this, and we need to find these. They're basically 2 separate operations. In general, it's a good idea to find the corresponding or the complementary solution first, just because it tends to be easier. And then we can work our way back and find the non-homogeneous part. In this case here, let's talk about the complementary solution. It would be the same equation on the left-hand side, standard form, but equal to 0 and not equal to the right-hand side. This is our finding YC. Well, we know what we do with this part. Remind ourselves that we assume that we have an e to the RT form. We get r squared minus 3r minus 4 equals 0. That factors as r minus 4, r plus 1 equals 0. And so our YC, let's go here, r is 4 and negative 1. Our corresponding homogeneous or complementary solution is C1 e to the 4t plus C2. This negative goes in the exponent, e to the negative t. And we see that that actually is quite straightforward. That leaves us next with the non-homogeneous part. So we found all of this in about 3 lines, love it. And then we go back and try to solve for the non-homogeneous solution type. That's going to be a bit more complex. We'll do it on the next page. So our non-homogeneous solution is definitely going to have exponentials times cos. So what's the building block there? And e to the t cos of 2t. And then you think of the differential family. If we have e to the t and cos 2t in our building blocks, if we differentiate this, we're going to get e to the t's times cos, and we're also going to get e to the t times sine of 2t's. But once we get to this stage, if we differentiate again, product rule will give us e to the t sines and e to the t coses, and we're back to this again. So in fact, all we need are those 2 ingredients, e to the t cos and e to the t sine 2t as our building block. To find a and b, we have to sub that into the differential equation. And to sub into the differential equation, of course, we need the derivatives of this proposed solution. Now this is where it gets a little hairier, so be prepared for a bit of writing at this stage here. We're going to have the derivative of the exponential, fortunately, is the same exponential, so we'll have e to the t cos 2t, so there's a product rule, plus when we differentiate the cos, we'll have 2, and it'll be negative e to the t sine 2t. And we'll, in addition to that, have b e to the t sine, differentiate e to the t, we get e to the t sine again, and then plus 2 e to the t cos 2t. All right, that's already 4 terms. Let's pool those together a bit so the derivatives on the next stage are a little bit easier. We have coses, so we have e to the t cos of 2t's, and how many of those? We have a of those plus 2b of those. And we also have the e to the t sine 2t. E to the t sine 2t, we have negative 2a's of those, and we have a positive b of those. And that's still the first derivative. Just tidying up there. And then what we're going to do is take another derivative with respect to time, and we'll get the second derivative. And that'll give us a plus 2b's. And we actually did this before. The derivative of e to the t cos is going to be this combination here. E to the t cos minus 2 e to the t sine plus minus 2a plus b's e to the t sines plus 2 e to the t cos 2t. And yes, this is how tedious it gets. As a little aside, once we start getting into these stages, I start looking a little bit at using computers to help out with the raw calculations, just because it's so easy to make silly mistakes. But these are the building blocks. This is what we have to use. We're going to tidy that up one last stage so that we have nice groups of e to the t cos and e to the t sine. We have e to the t cos. How many of those do we have? Well, we have an a plus 2b of them. And e to the t cos is here with a 2 out front, so we're going to have minus 4a's plus 2b's of those. And we're going to have an e to the t sine 2t group. And that is the sines here with negative 2 out front, so negative 2a, negative 4b's. And e to the t sine is here, so I'll have negative 2 more a's and plus a b. And that is going to simplify a little bit. That's negative 3a's plus 4b. And this is negative 4a minus 3b. My goodness. And now we have to sub this in to the differential equation. So in all honesty, what I usually do at this point is I do not write out this whole equation with all these terms because, oh my goodness, it's just so easy to make a typo, some other kind of mistake. I try to jump directly to the next step, which is equate the coefficients of, in this case here, it's e to the t cos 2t and e to the t sine 2t. I'll squeeze that on here because I think it's valuable to see them all on the same page. If we look at the coefficients of e to the t cos 2t, this is in the differential equation. We have in the differential equation y double prime. Y double prime has e to the t cos 2t's in it, absolutely. In fact, it has negative 3a plus 4b's of them. And then we have minus 3 times y prime, but only the coefficient of e to the t cos. Y prime, here's y prime, e to the t cos, a plus 2b. Minus 4, differential equation, minus 4 y's, and the y was simply a e to the t cos, so we have minus 4 a's. What did we have on the right-hand side for e to the t cos's? We had negative 3 of them. So not easy, but way easier than trying to write out the entire solution or the entire left-hand side of the equation and right-hand side. Because we can do exactly the same thing with the coefficients of the sine 2t's in the differential equation. Y double prime, e to the t sines has minus 4a minus 3b's. Minus 3 y prime has a minus 2a plus b as its sine e to the t sine coefficient, and last but not least minus 4 times the y is just a b e to the sine 2t. On the right hand side you'll notice there are none of the e to the t sine 2t's, and so that just means the coefficient is 0. Just for contrast, go back to the last page. Don't you miss solving the homogeneous part? 3 lines and you're done. Ugh. Yeah. Back to this. Having arrived at this system of equations, we'll copy them to the next page and then try to solve them there. Gathering our a and b values, we have minus 3a, minus 3a, minus 4a. That's minus 10a overall. And plus 4 minus 6 is minus 2b's. In the second equation, we have minus 4 plus 6 a's, which is plus 2 a's, and we have minus 3 minus 3 minus 4 minus 10 b's. That all adds up to 0. We can then take those equations, multiply by 5, and add them. Then I'll have minus 10 plus 10. We'll also have minus 2 plus 5 times that is 50, so I'll have 52 b's negative. That's going to equal negative 3. So b will be equal to negative 3 over negative 52, or 3 over 52. Having found the value of b, we can then go back to either of the other equations and start solving for a. Let's grab this equation here. It looks like it's got simpler coefficients. And in there we have 2a is equal to 10b's, so a is going to be equal to a half, or better yet, just 5b's, which will be equal to 15 over 52. All right, and that gives us the non-homogeneous part of our solution, thank goodness. Putting the pieces together, we had the a with the exponential times cos, so 15 over 52 e to the t cos of 2t. Then we had b, which is the 3 over 52 e to the t sine of 2t. And so, at long last, the general solution, remember this is just one part of the solution, the general solution is our non-homogeneous part, 15 over 52 e to the t cos 2t, 3 over 52 e to the t sine 2t, and that is going to get added to the complementary solution which we found earlier, c1 e to the 4t, c2 e to the negative t. c1 e to the 4t plus c2 e to the negative t. And so that's our complementary solution there. You'll notice this is still general because when we put all the pieces together, it's a second order equation and there are two constants we don't know yet. But we also have this part of the solution that corresponds to the right-hand side, and in particular, what would happen if we subbed in that y in for y and y prime and y double prime to get the 3 cos t e to the t cos 2t. So that is one full and complete general solution process for a non-homogeneous and a fairly complicated non-homogeneous differential equation.